Hello everyone, I'm Shifali, and for my seminar project, I worked on distributed learning in wireless sensor networks. Let me begin by outlining the structure I will follow in this presentation. First, I will give a brief introduction about WSNs or wireless sensor networks. Then, I will tell you guys about the research problem I worked on. Then, I'll talk about various models of learning in wireless sensor networks, the experiments I performed, and the results I obtained. So first and foremost, what are wireless sensor networks? They are a network of sensor nodes that sense physical phenomena in a region of interest. So each sensor node senses phenomena like heat, temperature, sound in its region of interest. It then shares this local information with other nodes, and in this way, a global understanding of the region of interest is built. So now we know that WSNs can make inferences about any region of interest. Therefore, the development of WSNs was initially motivated by military applications like battlefield surveillance, but now these networks are widely used in many industrial applications like industrial process monitoring, weather monitoring, and so on. Now let us come to the problem at hand. We have M sensors randomly deployed about the environment. Each sensor acquires training data from its environment. For example, here X could model position and Y could model an environment parameter such as temperature. In our setting, the joint probability distribution Pxy is not known. So we seek an approach that minimizes the traffic flow in WSN, which means that we want to minimize the amount of data transmitted from one sensor node to another in the network. And we want to predict an output for a new input in this setting with reasonable accuracy. We have different approaches for learning in wireless sensor networks. The first approach we'll be looking at is the centralized approach. Then we will look at the distributed approach. In most of these approaches, I will talk about a fusion center. Now this refers to a common center where all the data from the sensor nodes is collected and the processing of information is carried out to make an inference. Now coming to the centralized approach, this approach can be visualized in this figure. Here SI refers to the ith sensor node, X refers to the feature space, and Y refers to the output space. So in this network, every sensor node sends its complete raw data to the fusion center. The fusion center then applies a learning algorithm on this collected data to derive an inference. Although this approach is quite simple and straightforward, it has major drawbacks. Because every sensor node is sending its entire data, it makes this approach really costly in terms of bandwidth. And because every sensor will communicate with fusion center, this approach is really costly in terms of energy as well. These reasons make this approach quite infeasible in practice. And because our focus is on designing learning algorithm that respects the constraints on energy and bandwidth in wireless sensor networks, we must do better. We can move towards a more decentralized setting where instead of sending its entire data, each node just sends a summary of the data. And also by just making a simple improvement over the centralized setting, we can achieve much better results. This improvement we will look at in the clustered approach. Now with this approach, we are moving towards a more distributed technique for learning in wireless sensor networks. The improvement we were talking about in the previous slide is that instead of all sensors communicating with the fusion center, only a subset will communicate with the fusion center. So in this approach, the sensor nodes are divided into subgroups. Each subgroup is assigned a cluster head. So cluster heads retrieve the data from the sensors in its group, filter this data, and send the fusion center a summary of this data. The fusion center then uses kernel methods for learning and deriving an inference from the data. So in the project, I implemented both the centralized and the clustered approach. The steps I followed to implement the clustered approach are as follows. First is the data preparation, wherein I obtained the data and did some pre-processing on it. Then I clustered the sensor nodes based on their location. Further pre-processing is done within each cluster to obtain the summary statistics that are then sent to the fusion center. At the fusion center, further processing is done to make an inference. I use the data provided by the city of Melbourne. It is open data that is available at this link. It consists of environmental sensor readings. So the sensor nodes are measuring the maximum, minimum, and the average temperature, humidity, and light at various locations in Melbourne. An initial data analysis revealed some interesting things. So now let's see. Here we have a 3D plot. Here X models the longitude, Y models the latitude. So the XY plane models the position where the sensor is located. The Z axis models the average temperature. Here the blue circles represent the average temperature measured by the sensors at different locations and times in Melbourne. So from this plot itself, we can see that there are around 3 clusters of sensors in the city. Next, we move on to clustering the sensor nodes. For this, k-means was used. I also did this using DBScan, and from both, similar results were obtained. With k-means, the number of clusters need to be specified in advance, for which a preliminary data analysis is necessary. Here we obtain 3 clusters. Here the blue cross represents the cluster head, and the green circle here represents the optimal location for locating the fusion center. So now, once we have obtained the clusters, the next task is to obtain the summary statistics from each cluster. As summary statistics, a locally learned rule or some data that is particularly informative can be used. We have chosen support vectors as summary statistics for our model. So support vector regression is implemented at each cluster. The features used are latitude, longitude, average humidity, and average light, and the output space has temperature. Now once support vectors are obtained at each cluster, they are sent to the fusion center for further processing. The fusion center uses the support vectors collected from each of its cluster heads, and it uses them as input features for its learning algorithm. Now we can see that the clustered approach saves significant cost of transmitting all data to the fusion center. But the question is, how does that fundamentally affect the quality of estimates? To find that out, I run an experiment. Now from this table, we see that when the number of samples are low, both the centralized and the clustered approach perform equally well. But as the number of samples increase, the centralized approach performs slightly better. Now here, the score is the R-squared score, and the best possible score is 1. For example, let's consider the case when the number of samples are 30,000. Here the centralized score is 0.51 and the clustered score is only a slightly lesser 0.47. So this performance can be attributed to the observation that only the support vectors play a role in the estimation obtained in the clustered case, and the other observations don't affect it. Here you can also see a column of support vectors. So for again this case, 11,301 are the number of support vectors that cluster 1 sends. 2,623 are the number of clusters that the second cluster sends, and the third cluster sends around 17,025 support vectors. So the fusion center receives around 15,700 support vectors. In comparison to that, the centralized approach sends all the 30,000 samples to the fusion center. So clearly we can see that with the clustered approach, we are sending around 48% less traffic to the fusion center. But can we do better than this? Can we minimize the traffic flow further? We see that within a cluster, the communication is quite inexpensive because the data is sent over short distance. But sending data from the cluster to the fusion center is more expensive. So if we limit this number of support vectors sent from the cluster head to the fusion center, we can minimize the traffic flow in the network further. So now let's conduct an experiment where the support vector traffic is decreased and the performance of the model is then evaluated. So we have the dataset with 32,000 entries, half of which are used for training. So we begin by allowing the support vectors sent from each cluster to be 16,000. This means that a maximum of 16,000 support vectors are allowed to be sent from each cluster to the fusion center. So now when we see that when we decrease the number of support vectors allowed to about 13,000, the performance is not at all affected. The R-squared score still remains 0.478. This means that every cluster is sending less than 13,000 support vectors to the fusion center. Decreasing the number of support vectors further, we see that the R-squared score starts decreasing. From this, we can infer that at least one of the clusters is now not able to send its complete list of support vectors. Till about 15,000, we can see that the performance is decreasing, the R-squared score is decreasing, but the performance is not affected much. But if we reduce the number of support vectors allowed further, the performance is severely affected. From this, we can possibly infer that now none of the clusters are able to send a significant portion of their support vectors. So, this performance is also summarized by the slides. It just says about the initial number of support vectors and in each case what is happening. So from this graph of number of support vectors versus the R-squared score, this effect, the decrease in performance, can be visually observed. R-squared score is constant initially, then decreases slowly at first, and then decreases rapidly. So from this, we can infer that the number of support vectors sent from a cluster should be reduced only to an extent. So initially I talked about the centralized algorithm. Its drawbacks arise because of its inherent assumption that sensor nodes can communicate with the fusion center but not with each other. With the clustered algorithm, we overcame those drawbacks, and the experimental results confirmed that clustered approach reduces traffic in the network to a large extent when compared to the centralized algorithm. So for the data set on which the experiment was performed, 47.8% reduction in traffic was observed with only a slight decrease in performance. Well, clustering sensor nodes in this case depends quite highly on the location of sensor nodes itself, and k-means and db-scan both performed equally well for the current data set, but this might differ with some other data set obviously. We also came up with a technique to minimize traffic in the network based on support vectors and then further evaluated it experimentally. As I'll be continuing this project in my thesis, the next steps for me includes experimentally evaluating another promising approach, the alternating projection algorithm, with the current centralized and the clustering algorithm. Now, this approach, the alternating projection approach, is a message passing algorithm. It is quite different from the clustered approach because here the data is not collected at a fusion center. It's not collected at one point, and hence the fusion center may or may not even exist. So now in this approach, each of these sensors represented by the small si, they maintain a message variable z, and a sensor calculates its global estimate by querying its neighbor's local message variable data. So for example, S5 will calculate its global estimate by querying S3's and S6 z, the message variable. And further, when this global estimate is calculated, the sensor will update each of its neighbors' message variables. Then the neighbors will pass along their updated message variables to other sensors, and in this way the information is propagated globally in the network. So now after a comparative evaluation of the alternating projection algorithm and the clustered approach, I can also find the optimal location for positioning the new sensors and find the optimal frequencies at which the sensors must make the measurement. I can also test the approaches on a more extensive open data set, but in essence the technique will remain the same. With this, I come to the end of my presentation. Thank you all for listening.